Well, I am Riofrio, and I've been working on data processing using cloud computing. And as part of my research, ongoing research with the RACE lab here at UCSB, I've been working at JPL, mainly with Kawhi Shams. And the Jet Propulsion Laboratory is a NASA field center. And perhaps most famously, they're known for their Mars rovers. And this is a picture of the new Mars rover. I got to see part of it before it was shipped to Florida. But this new Mars rover is called Curiosity, and it will be sent to Mars in December. I've been working with another mission. It's a neuroscience mission, and it's called CAR. CAR stands for Carbon in Arctic Reservoirs Vulnerability Experiment. And what they're doing is they're studying the carbon budget in the Alaskan Arctic to gain a better understanding of the carbon cycle in our world, and maybe get some insights on things like global warming and stuff. So they will be sending an airplane 3 times a year, and it will go there multiple times in each period throughout the year. And it will be taking measurements of the air below. But one thing that you're seeing a lot of in new missions at JPL and NASA, and even in industry, is that there's a lot of data. And there's a lot of processing to be done with this data. In CAR, there are 7,200 soundings coming in from the airplane every day to JPL. Each of these soundings take about half an hour to be processed through, half an hour on average, to be processed through a program called the Level 2 Full Physics Processor, which takes in the sounding data, which is spectrum data, and calculates or estimates measurements of concentration of carbon dioxide, carbon monoxide, and methane, so they can study it. If you try to do all these 7,200 soundings, one after the other, it would take us about 5 months to run on one machine that has 1 core, if it takes half an hour. If we try to have all of 1 day's worth of data ready in 1 day, it would take us 20 machines, 20 machines. And if we want to have this even faster, say ready in a couple of hours, it takes us hundreds of machines to be able to run this. And the thing is that we don't want to buy these machines because they will not be used throughout the day or throughout the year most of the time. This kind of property is called burstiness, and it is found in many places. In industry, it's found, these are just 2 examples, and there's multiple of them, Amazon.com and Netflix. In Amazon.com, for example, there's a lot of people going to Amazon.com during Christmas time, buying gifts and stuff. So they need a lot of processing power during December that they won't need throughout the rest of the year. And Netflix has a similar property throughout the day because most of their customers are here in the United States, and a lot of people watch movies in the evenings. So what we need is something that allows us to use a computer for only a fraction of the time and only pay for that amount of time. In other words, we want to have so that running one machine for 1,000 hours costs the same as running 1,000 machines for 1 hour. So this is where cloud computing comes in. Cloud computing, there are multiple services that there are. There is storage services, and there's database services, there's messaging services. Perhaps most useful for us is computing services in which you rent computers. But all of them have the property that we only pay for what we use. And that's Amazon services. Google has also cloud services. Microsoft has cloud services, among many other companies. And we also used another feature of cloud computing called bit-based pricing. It was first introduced by Amazon. Actually, I don't know of any other company who offers this right now, but I'm sure there will be, in which it works like this. So you set a maximum price, it's called your bid price, that you're willing to pay for your computer per hour. And as long as the market price stays below your bid price, you will get your computer. As soon as the market price goes above your bid price, your computer will be terminated. And this introduces some complexity to your workflow, but it's much cheaper. In fact, using cloud computing and bid-based pricing, we have calculated that we can run 1 day's worth of soundings just spending $200 or so. And it costs the same whether it takes 2 months or 2 hours. So that's really powerful in cloud computing. So to do this, we decided to use a framework called Polyphony. It was developed at JPL. They published a paper in it last year. And it basically served as the basis for what we did. And I'll talk about it a little bit more later. But I helped develop it, and a lot of the contributions that I made during this summer will be integrated into Polyphony and be used in other missions. So during the summer, there were some challenges in trying to get the level 2 full physics processor to run on the cloud among multiple machines for it to be scalable and for it to be fast. We wanted to run in just a couple of hours, and we wanted it to be cheap. So we started with a very simple architecture. This is a simple architecture in which you have a head node, and you have multiple slave nodes. And when you want to run some jobs, you tell the head node, here are some jobs, and it will push the jobs onto these slave nodes. It'll tell them, here's some jobs to do, here's some jobs to do. But the cloud is dynamic, and you're constantly removing nodes, and you're constantly adding nodes. And how will the head node know that that node was terminated? Or how will it know how to contact those new nodes? There are some solutions, of course, but we found that a very good solution is to reverse it around and to use polling, so that when a new node comes in, it is asking the head node, do you have a job for me? Do you have a job for me? And when the head node has a job, it'll respond with the appropriate job. So this works alongside with queues. So the head node gives an internal queue of all the jobs that it needs to do. And when it assigns a job to a slave node, it checks it out like you check out a book from the library. And it waits. And if the slave node doesn't get back to the head node in, say, 2 hours, then the head node will assume that it has failed and assign the job to someone else. So that's how it works basically. But I told you earlier, and this is dealing with failure, I told you earlier that each of these soundings take about half an hour to be run. And they really range between 10 minutes to an hour and a half. And the problem is that our nodes can be terminated at any time, by us, by hardware failure, or if we're using bit-based pricing, they can fail. And we don't want to wait the whole 2 hours, the timeout time, for us to restart our process. We want to quickly adapt to changes in the topology of our cluster. So we fix this by using heartbeats. The slave node, when it's doing a job, it's sending constant messages to the head node, saying, I'm still here, I'm still doing the job. And if and when this slave node fails, it will stop sending messages so that the head node can quickly react and assign the job to someone else, say within 5 minutes. So that helps us bring our jobs, that helps us process our jobs much faster, sorry about that. So that's how we deal with failure. Another thing that we had to deal with was a data transfer. So I told you earlier that the airplane sends the data from the airplane to JPL, and then we need some way to get the data from JPL to the cloud, and then the output from the cloud to JPL. So one way that we could think of doing this would be to have the slave nodes get the data from a node at JPL. But this won't work because we don't want any node outside of JPL accessing nodes at JPL. You know, they're a government organization, and it's just not safe. So another way of trying to do this would be to have the node at JPL send the data to the slave nodes. But then this won't work either because we don't have any way of knowing what new machines were added and what machines were terminated. So instead, we have the data come from JPL to the head node, which we know about. And then when a new machine comes in, it asks, you have a job for me. And then the head node will answer, yes, here's a job and here's some data. So that's how we deal with data transfer. And finally, perhaps most importantly, is what do we do when we want to run 100 machines or 1,000 machines? Because that's why we're using cloud computing, or at least that's half of what we're using cloud computing. So as you can see here, we just have like a dozen machines, and this head node is already looking pretty crowded. It's one central point of failure, and if it's not fast enough, or if it fails, our whole workflow has just failed. So we need a way to distribute them. So the first thing that we distributed was the file system. We used a simple storage service from Amazon, which is a cloud storage service, which basically consists of a bunch of machines, which gives us storage. So we don't have a central point of failure anymore. But we still have this head node. So we need some way to distribute that. And the way we did this is by using polyphony. polyphony was used among all of it, but perhaps this was the most important part of why we use polyphony. And it uses messaging services like SQS, Amazon SQS, simple queue service, to distribute the control logic from the head node among all of the slave nodes, so we don't have a central point of failure anymore. So those were the challenges that were present during the summer when I was trying to develop a solution for CAR, for the processing in the cloud. And as I mentioned earlier, we used the framework of polyphony. It was developed at JPL, and it has optimized support for cloud services like S3. It has support for hybrid clouds, which means that you can run some of your jobs in-house and some of your jobs in the cloud. But perhaps most importantly, it is a central place where missions at JPL can use this framework and avoid the duplication of work, so that they can use the lessons that we learned during the summer in their own processing needs. And hopefully it will be able to be used in other places, in NASA and even in industry or academia. It has been used in ATHLETE, in Mars Exploration Rovers, and in Mars Science Laboratory, which are just some missions at JPL. And it will hopefully be used in other missions like OCO2, which is another Earth science mission. And actually, a lot of my work will probably go into that as well. So I have a lot of people to give thanks to. Those are a lot of people at JPL that I worked with. I especially want to give thanks to Kawhi Shams and Tom Soderstrom, which was my mentor and my super mentor. And then to Chandra Krins, Raj Chauhan, and Chris Bunch for their support. And Eric Lubin and Philip Gire for managing this program, and to everyone else who was involved. So I've learned a lot during the summer, and hopefully my contributions will be able to be used among JPL and elsewhere. So thank you. Any questions?
So you said quickly that it cost $200 to do all this processing when you could use it when you were using spot instances.
Yes.
What does that compare to if you didn't use the spot instances? I didn't see the difference. How much are we saving by using spot instances?
About double.
Twice.
Yeah, so it would cost about $400 without spot instances.
Yeah. The other question I had is, all that communication you're doing, the heartbeats as well as moving the data in and out, you're being charged for.
Yeah.
Did you look at sort of an overarching cost model for the different charges that the public cloud is applying to you, and to think about how often you want to do heartbeats or how often you want to move data?
Right. We didn't, but I am pretty sure that it will not add more than 50% to our costs. And the main thing was to the scale of the cost, right? $1,000 versus $100. That was the main point of that. So.
I know that right now the government has been especially pushing on many of the departments to go to cloud computing, but I know a lot of them have been resisting it because of possible security breaches and things that have happened in the past. What can you ensure that this data would be secure, or is it really not something to worry about?
Mm-hmm. I think there are two issues. There's security in the sense that we don't want to lose our data, and then there's security in the sense that we don't want other people to see our data. So in the sense of we don't want other people to see our data, we do encrypt. All the communications with the cloud services are encrypted. So that's encrypted. And then the files that are stored on Amazon S3 are protected by them. We don't encrypt them as of now because we trust it enough. But if it became a problem, and I don't think it will, we can encrypt them and then decrypt them on the slave nodes. But that might just introduce complexities that are really not needed. In terms of losing our data, S3 is redundant. It has our data is replicated among two data centers in one region. So right now we've been using San Francisco. So there's two data centers in San Francisco that our data is replicated amongst. And actually, I was working right next to another intern who was working in ways to distribute data even further. That was really good research that could be made. But again, we haven't handled those issues yet. We don't expect to have any problems like that. in fact, sorry, I forgot about this. The data that we send to the cloud is only a replica of the data we already have at JPL. So we're not going to be losing the data.
You described how you went from a system where the node is being told what to do to a node kind of volunteering. Like volunteering, saying that I'm ready to kind of do the job. What would be a better name for it than slave nodes? Doesn't sound like slave anymore.
I call them worker nodes.
Okay.
Yeah, I figured it might be confusing if I switch terminologies in the middle of the presentation. So.
Is there a limit to how many of the slave or worker nodes you can have and still sort of process data in a timely manner?
Theoretically not. And the thing is, we're hoping to be able to, bring up like 3,000, actually no, 7,000, as many as their standings, machines to be able to do this in just a couple of hours. We haven't actually tested it, but we don't think it'll be a problem because of how the control logic is distributed among all of the slave nodes.
I guess it's kind of back to the security concern, but is there a way to make sure that the worker nodes delete the data that you've given them or the control logic in case you're handling more sensitive data than this?
Say that again.
Sorry, so is there a way to, because you give the data and the control logic to the worker nodes, right?
Yeah.
Is there a way to insert that they remove the data once you're done using that?
So, first of all, the worker nodes are pretty short-lived.
Mm-hmm.
So the way I envision this workflow working is that the worker nodes will only be up for 2 hours, and then after that, all of the data will be destroyed that was in the worker node.
Okay.
So in that sense, there's no problem.
So it's not like the worker node is a computer that you're saving data to, it's like a virtual machine that you're saving.
It's in fact all of the machines that are there are virtual machines, except the node at JPL. Maybe, I don't know. It depends.
How do you envision, so if you are having to duplicate it, let's say to protect from loss or security issues, and that duplication is costing money, and the more times that you duplicate it, then that keeps adding costs. How does it eventually get to where we're doing cloud computing, but the cost is essentially not the real issue, not the driving force?
Mm-hmm. So you're talking about the replication of the data stored in S3? Or in that
I guess
storage
so you were
service?
kind of describing how if we're going to, maybe we can have multiple replications going such that if this one was compromised, we're okay because we still have this one going on. But that's doubling it, right? And so then that essentially paying for each one.
Right.
And eventually, I guess I'm wondering, is the reason for all of this actually speed or the cost?
It's both. It's both, especially because Carve is a pretty low cost mission. But we also want speed, right? So there are two things. The computation themselves, we don't want to replicate them, because that would be just wasting money. In fact, we can just run all of our processing jobs in San Francisco, and if for some reason San Francisco goes down, then we can just start them up again in the East Coast. And it would just take double the time as opposed to whatever time it would take to replicate non-cloud computing or non-virtual machines.
Okay, thank you, Andres.